and inductors. Kate School has a demonstration transformer pictured alongside. She connects a 12,000 turn primary coil to the main supply 240 volts. So from this we know that this is the NP because it's the primary coil and the number of turns, and this is the VP because it's the voltage for the primary coil. Question A. She connects an AC voltmeter to the blue coil. Calculate the RMS voltage she would measure from the 600 turn secondary coil. So all we're going to do is find the voltage, the secondary voltage, and we've got the secondary number of turns. So all we're going to do is plug it into this formula right here. Plug those values in, you get 12 volts out, and you're going to make sure you include the units. The two coils are held by a ring of laminated soft iron which runs through the core of each coil. So it's got two parts. Explain why an AC voltage in the red coil produces an AC voltage in the blue secondary coil. So the main thing is when there's an alternating voltage in the primary circuit and the two circuits are linked, if there's an alternating current in the primary coil, it's always going to cause an alternating magnetic flux in the primary coil as well. That's just how it works. And because they're linked together through the iron ring, the changing magnetic flux in one is going to cause a changing magnetic flux in the other. So how the system responds is it produces a back EMF to oppose a change in the second coil's magnetic flux. So as a result, there has been a change in the change in the AC voltage in the primary coil has produced an AC voltage in the secondary coil. So that's all you need to write for that. It's the same thing every year. Just learn that and you'll be sorted. The coils are wrapped around an iron ring. So because the coils are wrapped around an iron ring, they can pass changing magnetic flux between them, and so they can change the voltage output. So it's just simple answer, same thing every year. They'll just change the object they're talking about, but it's easy, just memorize that. Okay, see. Kate connects the 12,000 turn primary coil in a circuit with a 12 volt battery and a 12 volt car headlamp bulb. Cause of the still linked with iron. Okay, so that's how you know it's still an inductor. Explain why the headlamp bulb only comes on after a slight delay. So also if they're asking about a slight delay, you also know it's about an inductor because they always have that 5-time period delay till they reach maximum current. So this is what I've written here. All you got to know is that when there's the changing magnetic flux like before, there's a back EMF produced to oppose it, right? Shown by this formula, and it's always going to slow down the current till it reaches its max value. But as the change in current is decreasing over time, because there will be less back EMF produced to oppose it. So yeah, and it always reaches its maximum value after 5 time periods. So then you can just chuck it in this formula. You always just chuck in formulas if just to help out your understanding and let the marker know you know what you're doing. Cool. So turn on after a slight delay. And you always say maximum brightness after 5 time periods when all 12 volts are supplied, rather than the inductor coil. Cool. Question D. The power station that supplies Kate's area generates 50 kilowatts of power. So kilowatts, you're going to make sure you convert that. So times it by 1,000. The transmission line near Kate's house carries 50 kilowatts of power to an industrial user. The voltage across the transmission line is 200 kilovolts. The resistance of the transmission line is 4 ohms for every kilometer. Calculate the power loss as heat energy across a distance of 300 kilometers. Okay, so this bit's quite easy, right? You've got the power, 50 kilowatts, and you've got the voltage, 220 kilovolts. All you got to do, calculate the current from that, which comes out to be 0.227 amps. Then all you're going to do is calculate the voltage loss every kilometer, which is just the value we just got, 0.227, times by the resistance, which is 4 ohms. That gets you 0.908 volts loss every kilometer, right? Then you're going to times that by 300 because there's 300 Ks. So that gets you 272 volts loss over the 300 Ks. And you just rearrange that again, plug that back in for power, timesing the voltage loss by the current, you get 61.744 watts. All you got to do is just round it to 3 sig fig. So, 3 sig fig for the power, gets you 62 watts. Then they've asked the comment whether this amount calculated is significant compared to a situation where the voltage is not stepped up to 220 kilovolts, but is transmitted at 25 kilovolts. So all you got to do here is just really restate what you've said, what you've calculated. Just not a very significant amount of loss for the 50,000 watts transmitted.